In the last video, we covered testing differences between means for independent samples. In this video, we'll cover testing differences between means for the same sample measured twice, or dependent samples. We'll also cover testing differences between proportions. Sometimes, particularly for evaluation research, we may want to determine whether a change in policy or a particular manipulation affected a group in some way. For example, we may want to know whether an antidepressant treatment improves depression, or whether a change in policy related to poverty helps to alleviate poverty. In either case, we want to compare the same group before and after the intervention. This is done in a very similar way to testing independent samples. Just as with independent sample t-tests, we want to compare the difference between the group means relative to the standard error, or the variation within the two groups. However, in the case of dependent samples, our formula for the standard deviation is a bit different, as you can see here. Instead of calculating the standard deviation for each sample and using those in our formula for the standard error, we now use D. D is the difference between before and after for each observation. As you can see in the formula, we want to square these differences and sum them. To illustrate dependent sample t-tests, I will be covering number 29 from your textbook in Chapter 7, which states, the following table shows the mean number of 911 calls to the police per month for 6 city blocks that set up a neighborhood watch program. Test the significance of the difference in the mean number of 911 calls to the police before and after the neighborhood watch program was established. Our research hypothesis is that there is a difference in the mean number of 911 calls to the police before and after neighborhood watch programs are implemented. The null hypothesis, which is what we will test, is that there is no difference in the mean number of 911 calls. As I stated earlier, in order to calculate the standard deviation, we need to calculate the difference as well as the difference squared. So I've created 2 columns to my table of data that I'll use to calculate those quantities. So for block A, before the neighborhood watch, there were 11 911 calls to the police per month. And after the neighborhood watch was established, there were 6 911 calls. So the difference is equal to 11 minus 6, or 5. I can copy this formula into the D cells for each of the remaining 5 blocks. Then, to calculate D squared, I simply type in the equal sign, select the D quantity, caret 2 to square that value. And again, I can copy that into the adjacent cells. As the formula shows, we need to sum those squared differences. So I will type equals sum, select the squared differences, and I arrive at a sum of 93. I also need the means for before and after the neighborhood watch. So under the before neighborhood watch, I can type equals average, parentheses, and select that column, close parentheses. And also copy that into the after neighborhood watch column. So before the neighborhood watch was established, there were an average of 15 911 calls to the police per month for these 6 city blocks. After the neighborhood watch, there were just over 11 calls. In order to calculate the standard deviation of the difference, the last piece of information I need is the n. As you can see, there are 12 pieces of data, and so it's tempting to think that the n is 12. However, that's incorrect. For our problem, the unit of analysis is blocks, and in this case, there are 6 blocks, A through F. So our n is equal to 6. Because the standard deviation formula is somewhat large, I'm going to calculate it in steps. So first, I'll calculate this term, the sum of the differences squared over n, which is equal to the sum we calculated divided by our n, which again is 6. Next, I'll calculate this second term, which is the difference in the means before and after squared. So equals parentheses the mean before neighborhood watch minus the mean after, close parentheses, squared. Now I can calculate the standard deviation of the differences in means. This is equal to the square root, or SQRT, open parentheses, of our first term, the sum of the differences squared over n, minus our second term, which is the differences in means squared. Now that we have our standard deviation, we can estimate the standard error. It is simply equal to the standard deviation divided by the square root of n minus 1. So the standard error is equal to the standard deviation that we just calculated divided by the square root of n, or 6, minus 1, which gives us a standard error of 0.4. At this point, we solve the problem in the same way that we solved t-tests for independent samples. Our calculated t is simply equal to the difference in means divided by the estimate of the standard error, or equals, in parentheses, the mean before minus the mean after, close parentheses, divided by the standard error. Now we have to compare our calculated t to a critical t, which we obtained from the table in the back of the textbook. In order to arrive at a critical t, we need to know the degrees of freedom. In the case of dependent sample t-tests, the degrees of freedom are equal to n minus 1, which is equal to 6, or n, minus 1, or 5. For 5 degrees of freedom, at the 0.05 level of significance, we obtain a critical t of 2.571. Because our calculated t, 9.55, is larger than the critical t of 2.57, we can reject the null hypothesis. In other words, it is unlikely that we would see this difference if there were no difference in the population means, or there is a difference in the mean number of 911 calls to the police before and after neighborhood watch programs are established. Next, we'll cover testing differences between proportions. Testing differences between proportions is similar to confidence intervals for proportions. Notably, we use the z distribution instead of the t distribution. In order to calculate a z ratio, we need the difference in the proportions and the standard error for the difference in proportions. Here's the formula for the standard error in the difference of proportions, and you'll notice that it includes a variable called p star. P star is the proportion for the entire sample When we only know the proportions and sample sizes for the two groups, we can work backwards and determine the overall proportion using this formula. To illustrate testing for differences in proportions, we will use this question. The General Social Survey includes a question, is there any area right around here, that is, within a mile, where you would be afraid to walk alone at night? Of the 15,178 males sampled, 23% answered yes. Of the 19,117 females sampled, 55% answered yes. Test the significance of the difference between the proportions of men and women who are afraid of walking alone at night in their neighborhood. So, from the question, we have the sample sizes for males and females, which I've entered here. And from the percentages, if we divide by 100, we obtain the proportion of men and women who answered in the affirmative. These two proportions and two sample sizes are all that we need to calculate a z-ratio. The first step is to calculate p star, or the total sample proportion. It is equal to, in parentheses, n1, or the sample size for males, times the proportion of males, plus the sample size for females times the proportion for females, close parentheses, divided by, and again we need to put the denominator in parentheses as well, the sum of the two sample sizes. This tells us that the overall sample proportion of individuals that are afraid to walk alone at night is 0.408. P star, as a proportion, will always be between 0 and 1, and it should fall between the proportion for our two groups. As you can see, 0.4 is in fact between 0.23 and 0.55. Now that we have our p star, we can calculate our standard error. As with the previous example, since the standard error formula is large, I will calculate it in parts. First, I'll calculate p star times 1 minus p star, which is equal to 0.408 times, in parentheses, 1 minus 0.408. Next, I'll calculate the last term, which is the sum of the sample sizes divided by the product of the sample sizes, or equals, open parentheses, our first n plus our second n, close parentheses, divided by n1 times n2, which, generally speaking, will be a very small number. Now we can calculate the standard error, which is equal to the square root, or SQRT, open parentheses, of p star times 1 minus p star, which we calculated above, times our ratio of sample sizes, which is equal to 0.0053. The final step to calculate our z-ratio is to take the difference in proportions divided by the standard error, or P1 minus P2 divided by 0.0053. This gives us a z-value of -60. The critical z-score, just as with confidence intervals, at the 0.05 level is 1.96. Since this is substantially larger than 1.96, we can reject the null hypothesis. The null hypothesis is that the proportion of men and women in the population who are afraid to walk alone at night in their neighborhood is the same. So by rejecting this, we are suggesting that the population proportion of men and women who are afraid of walking alone at night in their neighborhood differs. Specifically, women tend to be more afraid to walk alone at night than men.